Section 4, Development of Defects. Introduction. There are several factors that can influence the expected duration of rail service. The service life is affected primarily by the chemical composition of the rail, the track maintenance program, speed, and tonnage. All of these factors develop the vertical lateral head wear and plastic flow deformation of the rail head. Development of rail defects. Track maintenance program. The track maintenance program consists of any of the maintenance procedures that it can ensure the track maintain adequate support to reduce the amount of rail flexing, provide the proper friction control, and provide rail profile manufacturer that will consider influence the rail service life. Where the lateral wear occurs primarily at the gauge of the face, where the rail is located at the high side of the curve in the presence of the high wheel flange force. The vertical wear occurs at the rail head planing surface, where the wheel and the rail interact with the silical load and rail grinding patterns. Plastic flow. The plastic flow is a mechanical deformation of the rail head, can occur with high or low rail normally associated with the curves and carry high axle load operations. Plastic flow is a result of wheel-rail contact stress that exceed the material strength of the rail steel. Rail defects. Rail defects develop in any type of the rail of the rail well as a result of several conditions. The conditions normally will originate in the rail manufacture process. Silical loading and impacting the rolling stock, rail wear, or plastic flow. The development of rail defects can be influenced by the modern steel through the extensive maintenance program that will prolong the time frame before the rail is subjected to effects in the excessive wear plastic flow. This would include friction control methods or proper rail profile. However, it is impossible to accurately predict rail service life or defective problem. Figure shows the vertical plane and a horizontal plane through the and cross longitude of a rail section. The rail loading stress. Internal rail normally requires certain forms of rail stress and initiate the progression and develop the detective size defect listed below are terminology that can be used to describe the plane of stress in rail. Vertical plane stresses progress in longitude directional normal of the rail length. Horizontal stresses are along the rail. And transverse plane serves as a long cross section of the rail. Rail loading at the rail wheel interface. Vertical loading. Loading of forces applied with the wheel tread under the normal train operation. They are normally characterized in three components referred to as static load, dynamic load, and impact load. The static load is equivalent to the gross weight of the railway car divided by the number of the wheels. 160-ton railway car with 8 wheels has a static load of 20 tons. The static load can be influenced by the track curve super elevation. Dynamic load is an increase of the static load, the result from the train speed. This results from vertical dynamics associated with the car-truck interaction with the track geometry. Impact loading is an additional increased load over static and dynamic occurs when the wheel travels over a significant rail irregularity or a wheel that contains a flat spot. Note that actually vertical loading of the rail can determine the additional on the above components can be considerably greater than the normal static load. Lateral loading. The load forces applied with the wheel range and the high rail in the curved track is the result of wheel and truck curving force. In sharp curves, lateral loading is normally stable throughout the curve. However, the shallow curve of the tangent track, lateral load can occur as a result of truck hunting. Creep, a load force that is generated with a localized rail wheel defect interface with the roll action on the wheel. Longitude creep result with the traction applied with the rail head, wheel, and transverse creep forces result in the lateral movement of the wheel during the truck hunting. Rail stress. There's bending stress. Bending of the rail that occurs with the vertical wheel loading and lateral wheel loading. Vertical wheel loading normally results from loading between the supports and causing tensile loading, longitudinal stress in the rail base area and head web air fillet area. Lateral wheel load applies tensile load and longitudinal stress into the rail web area and head web area of the rail filled side. Thermal stress. The stress occurs in the continuous weld rails due to the thermal expansion contraction that occurs when the actual rail temperature increases above but reduced below the rail neutral temperature. When the rail temperature is above neutral temperature, compressive and longitudinal stress are established. While the rail temperature is basically normally temperature, tensile longitudinal stress is established, the stresses are drastically influence the rail flaw development. Residual stress. The stresses are a result of the manufacturing process, particularly with rollers, straight, and head hardening. This can also result in welded rails because of the different expansion and contraction of the steel that occurs during the welding process. Residual stress can be found in any location rail section and can exhibit high tensile stresses that can result in rail failure. Defective development identification. Defective development identification is determined by the type of the defect or origin direction of the development in relation to the planes of the rail section. They are identified in the transverse, vertical, and horizontal planes of the development. The defects that develop in the transversal plane relationship of the rail section are normally internal or in origin and are not visibly identified by the defective progression and penetration at the rail head. Internal transverse defective sizes can be only identified visually by breaking the cross-section of the rail in a press. A rail is broken and the transverse defect is measured against the cross-sectional area of the rail head. If half the rail head of the cross-section signs of defective growth, the defective is called 50% fracture. When the defective portion of the rail is examined, the certain characteristics provide information that will allow the typical type of growth identification ahead of the defect head experience. Transverse growth, normally referred to as three types of classification. Normal growth, defective development of the period of the time of the gradual stages. Normal development typically progresses into uninterpreted. The defect will show smooth and polished fracture with no granular structure. There are many numbers identifiable smooth and granular rings. This one shows the transverse defect showing smooth and polished transverse development. Figure 3. Figure 4 shows a detailed fracture showing normal growth pattern. Rapid growth signifies the development of numerous small stages. Small, polished, well-defined fracture is found in a rough granular surface, which shows the outline of several growth rings and gradual increase size. Figure 5 shows areas showing rapid transverse growth. Sudden growth. Significant recent development of a few large stages. The small, polished, well-defined fracture is surrounded by the rough granular surface, which shows that the outline of one or two growth rings, the distance between the rings, and will increase directly in the rate of the growth. Detail 6 shows a detailed fracture showing normal and sudden growth. You have the detailed fracture, normal growth, and a sudden growth. Detail 7 is a fracture on the normal, rapid, suddenly growth patterns. Normal growth, rapid, and sudden growth. Multiple stage ruptures. Defective develop an oblique, angular, longitudinal direction in the relationship of the rail section can also produce identifiable stage of development referred to as multiple stage ruptures. This is often seen as a bolt hole breaks or base breaks head and web separation. When a longitudinal angular defect shows a sign of various stages of development, each of the consideration separate stages of development, this is normally identified by the presence of pre-existing identifiable fatigue condition along the growth stage. Complete fracture referred to as the secondary development. There are also previous oxidization portions with a break of the normal, gradual, or non-oxide portion of a break. The oxide portion may represent an initial stage of development. Normal, granular, and non-oxide portion will normally represent a secondary stage of development. It is possible to have more than two stages of development before the complete fracture of the defect. The pre-existing fatigue condition is not identified with the fracture phase failure. Is commonly referred to as sudden rupture. Shows the vertical split head of the failure two-way stage, VSH, dark streak in the first stage development, and silver breaks off the second stage development, first and second stage. Shows a vertical split head showing the which VSH vertical split head showing two-stage development, first and second stage. Figure 9 shows welding failure shown. Welding failures first welding failures shown in first stage fatigue development and second stage rupture. The two stages of the welding fracture faces the oxidation first stage of the break and the total fracture in the second stage break and shown no discoloration. Figure 10 welding failure. Showing pre-existing fatigue and secondary rupture. Shows the pre-existing fatigue, secondary rupture. A rail batter. There are two significant types of rail batter that inspectors will normally encounter during the review of the rail defect. They are generally referred to as impact and fraction batter. Impact batter is rail breaking, exposing fracture face to the wheel impact of the rolling stock. Friction bearer is the result of sufficient rail sections separately allowing two fracture faces to make a contact or underload. Batter is defined as a significant rail end damage and smooth polish fracture face. Both of the types of batter can obliterate the matching fracture faces, preventing identification of underlying fatigue. Figure 11 shows an impact batter on a rolling stock from the rolling stock wheels. Chapter 12 shows the fraction batter from the fraction face of the contact. Section 5, FRA rail defects and descriptions.